Okay, so this is the same slide that we looked at last week, and this is the process that we use to undertake the actual statistical test itself to formally test our hypotheses. And remember, as I said last week, there's two different ways we can go about doing this. On the left-hand side, the process is if we were calculating these statistics by hand. On the right-hand side is if we were using a computer program like Stata, a statistical program, to do the calculations for us. If you were a researcher yourself, you would invariably be using some kind of computer program to do the calculations for you, but I am going to show you the hand calculation process, just hopefully to give you an understanding of what's actually happening when Stata does its magic. So for the one sample t-test, I'm going to be talking about this idea of the actual t-statistic itself being a ratio of signal to noise. And what I mean by that is the actual test statistic, which is the t-statistic, is a representation of the difference between the sample mean and the test value divided by the amount of variation in the sample mean. So what I mean by that is what we're doing to undertake this test is to compare our sample mean score, and therefore the population mean score from which the sample was drawn, to some kind of other external reference mean. So the first thing, that the signal representation, is the difference between the sample mean score and the test value, that external reference mean. And we divide that by the amount of variation or variability or dispersion around the sample mean. Because remember that there's always variation, there's always variability around a mean score. A mean is just the middle score or the average score, but it obviously doesn't capture every single person's score. So the t-statistic formula itself for the one sample t-test is written on the left-hand side there. And you can see that x bar represents our sample mean score, x being a representation of the sample mean. And then we minus our overall test value, and the test value is the external reference mean that we want to compare our mean to. And then we divide that difference by the standard error of the mean itself. So I've just written out on the right-hand side here what all of those things represent. And remember that the standard error of the mean is calculated by the standard deviation divided by the square root of the sample size. And the idea of the t-test being a signal to noise ratio is something that's common between the three different kinds of t-test that we'll be talking about. So it's looking at how big, how large the mean difference is, and also taking into account how much variation there is around the sample mean. So in this particular instance, if we wanted to calculate our one sample t-test, we can undertake this just by looking at the descriptive statistics. So x bar, our sample mean, is 0.521, and we got that just from the descriptive statistics table back on slide 9, I think it was. Our test value in this instance is 0.5 because 0.5 represents a proportion that's evenly split between the two. 0.5 is halfway between 0 and 1. So in this instance, if we were hypothesizing that the infants spent even amount of time between the two adults, looking at the two adults, then their proportion of gaze would be equal to 0.5 because that's half the amount of time looking at one adult, half the amount of time looking at the other adult. And the standard error of the mean in this instance, we can calculate just by using the standard deviation and the sample size. So our standard deviation is 0.177 divided by the square root of 32. And if we plug those numbers into our formula, then what we get is 0.021 as the numerator, 0.031 as the denominator, and that gives us a t-statistic of 0.677. So let's just talk conceptually for a second about t-statistics. As I said before, it's a ratio of signal to noise, the signal representing the difference between the means, in this instance, our population mean from which our sample was drawn versus that external reference population. And that's the signal, that's what the signal represents. And the noise is just the variability or the variance or the dispersion of scores around that mean. So if we have a t-statistic which is equal to 1, that means that the signal is equivalent to the noise, that the amount of signal we have about the difference between the means is the same, is in proportion to the amount of noise we have. The bigger the t-statistic in terms of the further away from 1 it is, the more of a signal we have in proportion to the noise, and therefore in very, very broad terms, the bigger the effect is. And remember that through the process of null hypothesis significance testing, like we talked about last week, what we're looking at in terms of getting more information from this t-statistic is to find out how likely it is, what the probability is that we've obtained this particular t-statistic if the null hypothesis is true. So let me say that again. The process of hypothesis testing, of formal hypothesis testing, is looking to see what the likelihood, the probability is that we've obtained this particular t-statistic if the null hypothesis of no difference between this population score and that other population score is true. What is the likelihood that we've obtained this particular t-statistic if the null hypothesis is true? And in order to calculate the t-statistic, and in particular get at that sense of probability, that probability of how likely it is that we've obtained this t-statistic if the null hypothesis is true, we need a certain number which is called a degree of freedom. And degree of freedom, or degrees of freedom, are numbers that represent how many particular numbers there are that are free to vary in a given sample size, in a given set of numbers. And the degrees of freedom for our one sample t-test are calculated by using our sample size minus 1. So in this instance, the sample size is 32. We have 32 observations. 32 minus 1 gives us degrees of freedom of 31. So we have 31 degrees of freedom in this particular instance. So we have a t-statistic of 0.67. We have 31 degrees of freedom. And if we were undertaking this process by hand, then what we could do would be to use a critical t-statistic table to find what the critical t-value is for a two-tailed test with an alpha of 0.05 with 31 degrees of freedom. And what I mean by that is, going back to what we were talking about last week, we can use a table of numbers which can tell us what the cutoff t-statistic is that represents a 5% probability of obtaining this particular t-statistic if the null hypothesis is true. Because remember back what we were talking about last week, that what our cutoff for kind of unlikely enough is, in terms of how unlikely it is that we've obtained this t-statistic if the null hypothesis is true, that cutoff that we usually use is a 5% probability, a 1 in 20 or 5% chance. So if we were to use one of these critical t-statistic tables, which you can find in your textbook, then we would find that the appropriate critical t-value for a two-tailed significance test with an alpha of 0.05, and remember alpha, which we can call our critical alpha, is our cutoff for significance, and with 31 degrees of freedom, that gives us a critical t-value of 2.0395. So the next step, what we want to do here is to compare our obtained t-statistic, which is 0.67, with that critical t-statistic of 2.04. I'm just rounding 2.0395 to 2.04. And we can see that our critical t is greater than our obtained t-statistic. And because of that, we do not reject the null hypothesis. We do not reject the null hypothesis that the proportion of time that the infants spend looking between the two adults is significantly different to half. We do not reject the null hypothesis. So that means that our mean score in this particular instance, in the population from which our sample was drawn, is not significantly different to our test value. So our critical t is bigger than our obtained t, which means we do not reject the null hypothesis, as I said, which means the mean is not significantly different to the test value. And remember that the process that we just undertook by doing that is to look to see the probability of obtaining a particular test statistic if the null hypothesis is true. And in this particular instance, there's quite a high probability that we've obtained a t-statistic of 0.67 if the null hypothesis is true, and therefore we do not reject the null hypothesis. There's not enough evidence that the proportion of time that the infants spend looking between the two adults is significantly different to half to chance. So even though our average proportion of time in this sample was 0.52, it's not big enough in terms of the difference from 0.5 and not systematic enough around that difference for us to say that it's not just due to sampling variability. So I'm going to go through that process again, but in this case I'm going to use Stata to do the calculations for us. And as I said before, this is what you'd commonly do most of the time. So this is our data set, as I showed you a few slides ago, and this is the particular variable that we're looking at here. This is the baseline proportion of gaze. Okay, so this is the data set that we're looking at here. So if we wanted to undertake a one sample t-test through Stata, then we can do it one of two ways. We could use the menu system, so we could use these menus up the top here, or we could write out the syntax, the written command to undertake this command, and we could put that into the command window. So I'm going to do it both of those ways, show you how to do it both those ways. If we were using the menu system, then we would go up to the statistics menu, down to summaries, tables and tests, across to classical tests of hypotheses, and then the t-test, the t-test mean comparison test. And then this menu would come up. We would select a one sample t-test up the top here. We would select the variable that we're undertaking this one sample t-test on, just using this drop-down menu here, and you can see I've already selected the baseline proportion of gaze. And then what we need to do is to put in the test value into this hypothesized mean box. So in this instance, our test value is 0.5 because we want to see if the infant spent a disproportionate amount of time looking at one singer compared to the other singer. If we were doing the same thing through the written command, then in the command little box, which you can see either down the bottom of your Stata screen, or if you've lost it, you can go up to the window menu and select command. So we type in the t-test command, which you can see is just t-test, and then the variable that we're undertaking this t-test on, double equals sign, and then our test value. So t-test, variable we're undertaking the t-test on, double equals test value. Once we do that, this comes up. So this is our t-test output here. And you can see we get a bit of information that's the summary statistics, just the summary descriptive statistics. And this is exactly the same as what we saw a few slides ago when we were just doing these summaries. Then we get some information about the actual t-test itself. We get a t-statistic, which you can see is 0.6744, just the same as what we did when we calculated it by hand a few slides ago. We have degrees of freedom, which is our sample size -1. 32 minus 1 gives us 31 degrees of freedom. And then we get 3 different p-values because there's 3 different ways that we could undertake this t-test. So I was talking last week about one versus two-tailed tests of significance. And what we see here is that the one in the middle, the type of t-test that I've highlighted here, this is our two-tailed t-test. It's a two-tailed p-value. And the left-hand side and the right-hand side one that both aren't highlighted, they're both of the one-tailed test. They're just going in different directions. So I said to you last week that for this entire course, for the rest of your psychology statistics education at Macquarie, if you keep on doing research design and statistics in psychology here, we are always going to be talking about two-tailed tests of significance, which means that the middle piece of information here is the only one that you need to focus on. Completely ignore this one and completely ignore that one. So what we have here, the first line is telling us what our alternate hypothesis is, and this is how we know that this is the right one for us. That the alternate hypothesis is that the mean score in the population from which our sample was drawn is not equal to 0.5, and exclamation point equals is Stata's way of expressing not equals to. So the alternate hypothesis here is that our mean score is not equal to 0.5, and that's the alternate hypothesis for our t-test, and that's how I know that this is the one that's relevant for us. This is the particular p-value on the bottom here. That's the one that we want. So p-value represents a probability. That's how it's expressed here. And this number, this 0.5051, is the probability that we have obtained this particular t-statistic if the null hypothesis is true. And remember that our critical alpha, our cutoff for significance, is a probability of 0.05, so a 5% chance or a 1 in 20 chance. This is a probability of 0.5, which is a 50% chance. So there is a 50% chance that we have obtained this particular t-statistic if the null hypothesis is true. And that's reasonably high. That's not small enough for us to reject our null hypothesis. And therefore, our conclusion here is that we don't have a significant result. Our p-value is bigger than 0.05, so we fail to reject the null hypothesis, just like Ryan Gosling's saying on the right-hand side here. We fail to reject the null hypothesis, and therefore we can conclude that the proportion of time that the infant spent looking between the two adults is not significantly different, that it's a relatively even number of amount of time that they spent looking between the two adults. That's our conclusion here. So remember that it's always the middle type of p-value that we want, and we can confirm that by confirming that the alternate hypothesis as is expressed here is the same as what we know we're testing in our particular t-test. Okay. If we wanted to write up, if we wanted to communicate the findings of this t-test, then there's a few different things that we need to make sure that we have in this kind of succinct communication of findings. What we need to make sure we're communicating, if we were writing this in a report or a research paper, we need to talk about what the actual descriptive mean is in our particular sample, so what our average score is in our sample. What the test value or the comparison point is, so what that external value mean score is that we're comparing our mean to. We obviously need to have the results of the t-test, and we need to interpret whether they're significant or not significant. So you can't just state the p-value, you need an interpretation of whether that means it's significant or not significant. And if you have a significant t-statistic, if your p-value is less than 0.05, so you have a significant result, you always need to talk about what the direction of the difference is. And that'll make more sense when we get to the next example for the independent samples t-test. So in this instance, we could write something like this. We could say that the results showed that the proportion of infant gaze time between the two adults at baseline, because that's the thing that we're investigating, was not significantly different to chance, and chance would be represented by a proportion of 0.5. We then report the mean score in our sample, which is 0.52, the standard deviation of that mean score in our sample, which is 0.18, the actual t-test results themselves, so t with our degrees of freedom in parentheses equals 0.67, and then our p-value, p equals 0.505. And then I have a concluding statement which interprets these results, which demonstrates that infants spends approximately equal time gazing at the two adults. So you can see in this one sentence, we've communicated a lot of information. We're talking about what the actual conceptual thing is that we're investigating, what the phenomenon is that we're investigating. We've represented what our test value, what our comparison point is, 0.5 for our one sample t-test. We've represented the descriptive statistics of our sample and therefore the population from which the sample was drawn. We've represented the actual t-test results themselves, and we've made some kind of interpretation about what it means that this particular t-test is non-significant. Okay, so that's one example of a t-test. The next thing that you could do, which I'm not going to do with you, but I very much encourage you to do on your own, is to practice going through that process again, but with a different variable. So the second example that you can use using the same data set, the same research context, is looking at the proportion of time that the infant spent looking between the two adults after the adults actually sing a familiar or an unfamiliar song. And this is formally the test of the research hypothesis that was back earlier in the lecture deck, that was testing to see whether infants spend more time looking at the familiar song adult compared to the unfamiliar song adult. So have a go at doing that yourself. The variable in the data set is this test proportion gaze to singer variable. And the actual test value is a test value of 0.5. And remember that if the proportion is greater than 0.5, if the value in the number is greater than 0.5, it means that the infant spent more time gazing at the familiar song adult compared to the unfamiliar song adult. So have a go and try it yourself.